All right, good morning. This is the 15.3 video. Hopefully it will be less full of distractions than the 15.2 video. My daughter's asleep, my husband's gone to work, my dog is already in here. It's not nearly as hot as the other day. My screen on my phone is clean. My throat is not hurting, so hopefully we won't have as much craziness going on with this video as we did with the last one, but who knows. Okay, so this is 15.3. It is on path independence, conservative fields, and potential functions. So it starts talking about here, and I didn't really mean to highlight these, but gravitational fields and electric fields are just some examples of fields. So here she's kind of talking about what we've already been talking about before in previous sections, these vector fields. But it's talking here about something that's new to this section in that certain types of functions, it doesn't matter what path that you take to get from one point to the other. So in the previous sections, we have seen that if you take a different path, you get a different answer. But in this particular section, these functions are of the form that you could take any path that you want to, but as long as you are going from the same point to the same point, it doesn't matter how you get there. So that's kind of the idea behind path independence. So they talk about it here. What page is this? 847. So you have D as your region in space. A and B are points in that region. We're looking at, again, at line integrals. And so it says here it usually depends on the path that you take, but for certain special fields, they are path independent. So that's what it's talking about here in this definition, that if it is path independent, what that means is that no matter what path you take, you're going to get the same answer as long as, again, you have the same starting and stopping points. And so if that's true, if a particular vector field, if the integral, so the integral would be path independent, then that particular vector field is conservative. So if you're talking about path independent, that's referring to the line integral of the vector field, and then the vector field itself would be conservative. So those, kind of path independent means conservative, path independent. And it talks here about where the word conservative comes from. It's a physics thing. And then at the top of the page, they say normally they use this for line integrals because it's an integral over a curve, which really should be called curve integrals, but I didn't name them. What they're telling you here is that instead of using this symbol, a lot of times they're going to use this. Remember, the A and B are points. So it's not like before you would have had this A and B, and that was bounds like on the T typically. So those were just numbers. Those A's and B's were numbers, bounds on the T. These A and B here are points, ordered pairs or ordered triples, they're points. But they use this kind of notation just to remind you that these particular integrals are path independent. So you don't care about the path, you just care about where you start and where you stop. Okay, and then here, if a vector field is conservative, well, this works both ways, so it's an if and only if. But if it's conservative, then you can find this lowercase f such that if you took the gradient of this lowercase f, it would be equal to that capital F. Or in the other direction, if this is true, then it's conservative. So if it's conservative, you can find this f. If this is true for this f, then it's conservative. So it works both ways. If and only if works in both directions. And so this lowercase f is called the potential function. So the potential function is the lowercase f such that if you took the gradient of it, you would get the capital F. So notice the lowercase f, it's a scalar function, meaning it's not a vector. Scalar function does not mean it's all numbers, but it's a scalar function in that it's not a vector. But when you take the gradient of it, then the gradient is a vector, and so that's how a scalar function is able to be equal to a vector because it's the gradient, which is a vector. Okay, so here they have the formula. This again, instead of the integral of the C, like this up here, they're using this to remind you that it's path independent. F is this, capital F is the same thing as the gradient of lowercase f if it's conservative. And then here, what this is showing you, notice this is saying the value of the function at the stopping point minus the value of the function at the starting point. So all you care about is where you start and stop. You don't care about the path that you took to get there. So this is different than what we were doing in the previous sections of chapter 15, because before we'd get different answers depending on the different paths. But if these are conservative vector fields, then we're going to get the same answer. So they have more details. Obviously, read this on your own later. This is page 840 here in this highlighted section. Then they have a couple definitions down here. So definitely read this whole thing. There's a lot of stuff to read in this section, but I'm just going to go over the definitions really quickly. I highlighted them so you can see them. Piecewise smooth we've talked about before. Well, smooth we've talked about before. I think we've talked about piecewise smooth. Smooth, if you remember, I think I have the definition here in my notes. Yeah. So smooth was the derivative was continuous and not equal to 0. So if it was for a parametric r is a function of t, then the derivative is continuous and the derivative is not equal to 0. That's what smooth was. All right, so piecewise smooth is curves that are made up of several smooth pieces connected together. So a bunch of individual smooth pieces connected together makes it be piecewise smooth. And then connected, a region, or this could be 2D or 3D, a region or a surface, is connected if any 2 points in that region or surface can be joined by a smooth curve that lies in the region. Okay, and then simply connected, here's the definition. I'll tell you a better way to think about it in a second, but here's the definition. Every loop in the region or the surface can be contracted, so gets squished in, to a point in D without ever leaving D. So here, this is simply connected because any 2 points in the region can be joined by a curve that lies in the region. That's two-dimensional. Here's a simply connected surface that's three-dimensional. These are not simply connected because, see, if you took this loop and you contracted it, so it's big, and then if it got smaller, contracted, you would leave the region at some point, because once you got to where this red loop was smaller than this hole, you wouldn't be in D anymore. So another way to think about simply connected, it's simply connected if it doesn't have any holes in it, basically, is an easier non-math way to think about it. So this donut also is not simply connected because, again, if you took this dotted loop and you contracted it to get smaller and smaller, once you were inside the middle of the donut, you would not be in the region anymore. So it's not simply connected. So connected, just this, again, non-math ways to think about it. Connected in math is basically what you think about regularly connected. It's all one piece, but then simply connected, basically no holes in it. Okay, so top of page 849, it's talking about the difference between connectivity and simple connectivity. There's a caution here, you need to be careful, so definitely read these on your own, but we're going to look at some theorems now. The first one is Theorem 1, fundamental theorem of line integrals. And this is basically what we were looking at over here. Notice here they're using the C notation, but if it is path independent or conservative, then all you care about here is the endpoints. And here's just a little bit more information about what the Riemann sums. And then here's a way, or a theorem about conservative fields being gradient fields. So here it kind of tells you what this theorem is telling you. There's a lot of theorems in this section. I'm just going to let you read them on your own. It'll make more sense when we do some examples. But here they're talking about a loop property. So this would be specifically, obviously, for loops or closed paths. And so when it's a closed path, notice they use this notation that we saw in the previous section where it's, indicating that it's a closed path. So here the line integral is 0 if it's a closed curve, and it would be conservative on that. Also, here they have some connections between Theorem 2 and Theorem 3 that you can look at. And then here is another theorem. Well, this is not really a theorem, this is a test, but you are going to use this one to test to see if a vector field is conservative or not. So if the question was, is it conservative or not, this is what you're testing. And so notice this is the same M, N, and P. From the previous section, they come from the F. And so you're just taking partial derivatives, and you have 3 separate pairs, and you're just making sure all 3 of these pairs are equal. If any of the 3 pairs are not equal, you would just immediately stop and say it's not conservative, but you have to keep checking all 3 of them until again, either they're not, one of them's not equal, and then you stop and say it's not conservative, or until you show all 3 of them are equal. Okay, and here just a reminder, that test that we were just talking about, if the domain is not simply connected, you can't use that. Page 855, again, kind of another warning, be careful, check the domain. And then here you have, they talk about this, how to check if something is exact. And they have the formula here again with these partial derivatives. And here they're talking about this test. Down here, this component test for exactness. So this is, notice the same thing. This is page 855. This is page 852. Same thing. So you're just checking the same thing. This would be checking for exactness though. Okay, so let's look at this in my notes. A lot of stuff in this section. Path independent. Again, the integral would be path independent. The field would be conservative. Here's just a couple notes. C is a curve. D is a region or a surface. Region 2-dimensional, surface 3-dimensional. But it has to be open, meaning it does not contain its boundary points. F is the vector field. A and B are points, again, not numbers. Points, we already talked about that. The potential function is that lowercase f. Here's that if and only if statement. And then here's that formula with just a couple extra notes. Again, you use the A and the B if it's independent of path. Again, they substituted these together because they're the same thing. And then here the path doesn't matter. You're just looking at the final position minus the initial position. All right, and then those definitions, piecewise smooth, connected, simply connected. And then we have the loop property and test for conservative fields and test for exactness, same thing. Okay, so I didn't rewrite it, it's the same thing. All right, so let's look at some examples now. So first, you are testing for conservative fields, so that's where you're checking those three partial derivatives, which ones are conservative and which ones are not. So we're gonna look at two of these. Number 2 is the first one. M is the thing in front of the I, N is the thing in front of the J, P is the thing in front of the K. So you're checking this again, hold on, is on page 852. These are the ones I'm checking. So I've done them in pairs. So first, here is dp dy, here is dn dz, those are the same, so I keep going. dm dz, dp dx the same, keep going. dn dx, dm dy the same. So all three are the same, which means it's conservative. All right, so you try by yourself. Number 4. This one's just, this one, there is no k, so that means the p is 0. So notice, if the p is 0, then dp dy, dp dx, dn dz, dm dz, they're all 0. So if that's the case, you're only having to actually check one of those 3 groups. Okay, so check that yourself and see what you think. All right, so here's the one you should have checked. I forgot to tell you to pause the video, but hopefully you paused the video. Here's the one you should have checked. So dn dx is 1, dm dy is -1. Those were not the same, so it's not conservative. All right, next group of problems. 7 through 12. This is page 856 if I didn't already say that. 7 through 12, find a potential function for f for the field, well, for lowercase f for the field capital F. So you're trying to find that lowercase f. This is, I don't know if you remember, I don't even remember where it would have been. I don't know if it was Cal A or Cal B, but remember when you were doing the, they would give you the acceleration function and you would have to go back and find the position function. So you would integrate the acceleration function to get the velocity function, and then you would integrate the velocity function to get the position function. It's the same kind of idea here, in that you're starting with the derivative and you're going back to find the original function, but because these are partial derivatives, it's significantly more complicated. So I've kind of written out steps as we go through this. So I'll show you the steps. I'm going to do one and then I'll have you try one by yourself. So this is number 10. Okay, so here's my capital F. So if capital F is equal to the gradient of lowercase f, the gradient of lowercase f is this. So capital F, which is this in component form, has to equal the gradient of f, which is this. So for two vectors to be equal to each other, you have to set them equal component-wise. So their I components are equal, their j components are equal, and their k components are equal. So what that creates is these 3 little mini equations here. All right, so what you're gonna do, this is just a process, and again, it has a lot of steps, so just walk you through it slowly on this first one and let you try one. You're gonna start, your goal is to find the lowercase f where these were the derivatives of it. So obviously some integrating is going to go on. It doesn't matter which one you pick to start with, but just for consistency's sake, I always do them the same way. So I always start with f sub x. So the f is equal to the integral of f sub x with respect to x. So you're going to integrate this with respect to x, and you're going to get this. But because you took the derivative with respect to x, there could have been a function of y or a function of z or a function of y and z that were on there originally. But if you take the derivative with respect to x, those are constants, and so they're going to go away and they're 0. So instead of adding a plus c to the end, you have to add a function, and that function could have been a function of y or z or both, because that would have been constant with respect to x. And so when you integrate, these are indefinite integrals, so they need constants, but now these constants are functions. And so if you did it with respect to x, that function could have been y or z. Okay, so you've got to have this on there. All right, so let's look at the rest of this. So that's my first guess at my lowercase f. I think it's xy sine z plus some unknown function g, which is a function of y and z, or one or the other. So now I have to figure out what this is, so I got to find this. So to find this, I'm going to take the derivative now with respect to y, because I already used the x, okay? And I'm moving on to y. So take the derivative of this with respect to y. So here, take the derivative of this. The derivative of this with respect to y, notice this is a function of y and z, so it's a partial derivative. The partial derivative with respect to y. And then from the previous page, from here, I also had that f sub y was x sine z. So this is f sub y that I got from taking the derivative of this. This is f sub y that I got from up here. So I set them equal to each other, and I solve for this g sub y of y and z. So that's just 0. So now that's the derivative with respect to y of g. I want to find g, so I'm going to integrate. So I integrate with respect to y. That was just 0. So the integral of 0 is a constant. But again, here, this could have been a function of y and z. I took the derivative with respect to y. So any functions of z would have been treated as a constant, and they would have gone away. So they could have been there, I don't know. So I have to add now a function of z. So here was my first attempt. Now I'm going to substitute in what I have found for my g. Here's my second attempt. That function plus, here's my g of yz. Now I'm going to take the derivative again, this time with respect to y. So take the derivative of this with respect to z, not y, with respect to z. Take the derivative of this with respect to z, so I get this. This is a function of one variable, so you can just use the prime now. So this is that derivative. Over here is the other f sub z, so I set them equal to each other, and again I get 0, again integrating 0. And this time, because it was just a function of z, this time it truly is a constant c. And so I'm going to put that all together, and so this, I didn't circle it, there's my final answer. Okay, so that should be circled. My blue pen is not handy, so I can't do it. But anyway, notice the work. So you're gonna, whoops, I didn't label this one, but this one is integrating. So your first step is integrating. I didn't write that. Integrate. Then you're gonna write what you have. Then take the derivative. Then integrate. Write what you have. Derivative. Integrate. Write what you have. So it's just back and forth, derivative, integral, derivative, integral, derivative, integral. And so you just have to, if you're not sure what to do next, see what you did previously and do the opposite. So start with integrating, and then derivative, integral, derivative, integral. So it's just keep track of where you are. You know, you need to do the opposite thing next. All right, so I'm gonna have you try this next one on your own. This is number 8. Okay, so pause the video, same thing. Try number 8 by yourself. All right, so hopefully you tried it. I'm going to go ahead and show you the answer so you know if you got it right or not. I did circle this one. Here's the answer. If that's not what you got, I'm going to walk you through it. If that is what you got, good job. Okay, so same thing. Capital F is equal to the gradient of lowercase f. So I didn't show the work where I set these equal to each other, but this vector equals this vector. So this equals this, and this equals this, and this equals this. So you get your little mini equations here. And then here's your first attempt at the lowercase f, so you start with integrating. So I'm going to integrate with respect to x, the f sub x. So when I integrate, that was a derivative with respect to x. So y and z were treated as constants, and so there could have been a function of y and z, so I've got to add that on there. All right, so here's my first attempt, is this function. So now I'm going to take the derivative. I already did x, so now I've already used x, so now I'm going to do y. Derivative with respect to y of this. Okay, so this is a function of two variables, so it's a partial derivative. So that's this derivative with respect to y. This up here is also the derivative with respect to y. So I set them equal to each other. And I solve, and I get g sub y is z. So now I'm going to integrate that to find just the g. So integrate with respect to y, and then that could have had a function of z on it, but that would have been 0 because it's treated as a constant, so I have to put that on there because I don't know. Now this is my g, so I plug it in to get my second attempt. Now I take the derivative. I had this derivative here too. So I set them equal to each other, and this is 0. Integrating 0 gives me c. So that's how I get this. So there's more of these later in the section. If this is not making sense, it's just one of those things that takes a lot of practice. So a lot of practice on these, but then it starts to make sense because it's just the same things. It's derivative, integral, derivative, integral. Well, it starts with integral. So integral, derivative, integral, derivative, integral, derivative, back and forth. Okay, let's look at the next group of problems. This is talking about the exactness. Show that the differential forms of the integrals are exact, then evaluate the integrals. So remember the exactness. That's on page 855 here. It's the same thing you were checking for conservative. So it's kind of like the previous section, 10 different ways to say the same thing. But here's your m, here's your n, here's your p. All the derivatives are 0, so of course they're the same. So it is conservative, but it is also exact. So since it's exact, then, and this comes, I don't know where this comes from. It comes from in the book. I was going to try to find it and show it to you, but I don't know. I don't want to waste time trying to find it. But anyway, if your integral here, if this function is exact, then it's equal to the derivative. Notice it's here, I don't know if you notice, it's just the derivative of f instead of the gradient of f, because these are not vectors anymore. This is a non-vector or scalar kind of situation here. So this is df instead of the gradient of f, but it's the same principle. Okay, so the value of the integral is just the value at the end point minus the value at the starting point. Notice they had that here. This would be the capital A, capital B. So capital A, capital B. This would be the starting point. This would be the stopping point. So you have the stopping point minus the starting point. So you have to find the lowercase f. So it's a different form, but the same principle as what we were just doing for the potential function. So where is this? I don't know where this is in the book. Yeah, here, this is coming from this, this is page 855, this box here, that's where I'm getting this from. It's easier to copy out of your book. So m is the thing in front of the dx, n is the thing in front of the dy, p is the thing in front of the dz. So this is, again, like the gradient vector, but it's not a vector. So you have the derivative with respect to x is the m, these two. The derivative with respect to y is the n. The derivative with respect to z is the p. So I'm using this notation just so you can see it's the same thing as what we were just doing. df dx is the same thing as f sub x, and so on. So you get these little mini equations. So it's the same thing. So if you want to pause the video, you're trying to find the lowercase f again, you can see if this is making sense. So pause the video now and see if you want to try this by yourself. All right, so let's work on this together. Integrate with respect to x. You get this plus some unknown function. So here's my first attempt. Now I'm going to take the derivative with respect to y, set it equal to the other derivative with respect to y, solve for this, integrate, get some unknown function of z, plug that in. This is my second attempt. Now I'm going to take the derivative with respect to z, set it equal to my other derivative with respect to z, solve, set it equal, solve, integrate. Hopefully you recognize this one. Do you recognize this one? It is, dun-da-da, tangent inverse. All right, and then you plug it all in together. So this is my potential function, my lowercase f. And so the integral equals the values at those two endpoints, the stopping point and the starting point. So I just plug those in, simplify, and I get a negative pi. So negative pi is the value of the integral. Here I'm actually doing the integral. All right, so let's try another one. This is 24. 24, evaluate this integral along the line segment joining 0, 0, 0 to 0, 3, 4. So I'm going to find that, what is it called? Oh, parametric function. So I'm doing the parametric equations, and then I'm going to get the R. So terminal minus initial to get the vector. Parametric equations because this is a line. So this is my R. And then I'm going to need the derivatives of these. Right here's x, y, z. So there's the derivative of x, y, z. And then here's my starting point, my stopping point. This was my integral. So what I'm doing now is here, see these dx, dy, dz, and plugging those in place of dx, dy, dz. And then for the x, y, and z, that comes from here. X is 0, y is 3t, z is 4t. Okay, so plug in for x, y, and z, plug in for dx, dy, dz. Then it becomes a function of t. And so this is just like what we were doing before in the previous sections where you're integrating with respect to t. And so you just get 18 here. So this is kind of a throwback to the previous section. All right, so last one. This one's long, has a bunch of parts, but here's going to be the exciting news. We're going to figure out that this is conservative, and then it doesn't matter. Notice this just so you can see where we're going with this. If you were going to do this the 15.2 or 15.1, I don't remember which one it was, but if you were going to do it the other way, you would have to do 3 totally separate problems because it's different paths. They both start and stop at the same place, but this one it goes straight there. This one it detours to the origin and then comes. This one it goes down, back, and around. So you would have to do 3 totally separate problems. However, if you can show that this is conservative, then it's independent of path, and then it doesn't matter what path it takes to get there. So they'll all be the same answer because they start and stop at the same place. So that's what I'm going to do. I'm going to first check to see if it's conservative. So here's my F. It looks like a lot of work, but that's just because I really spread it out and show all of my steps. It's really not that much work. So I'm going to check and see if it's conservative. So I'm checking all these. I did them separately because they were so long on different lines. But here's the first pair. They're the same. Here's the second pair. They're the same. Here's the third pair. They're the same. So F is conservative, which means you can find that lowercase f. Okay, so this is just checking to see if it is conservative. So I set up these little mini equations. These are my little mini equations, and then this is the same process before. So if you want to pause the video and try this on your own, trying to find the lowercase f, you can do that now. All right, so lowercase f, start by integrating with respect to x. Don't forget the unknown function of y and z. Here's my first attempt. Then I'm going to take the derivative with respect to y. Then I'm going to set this derivative that I just found equal to this derivative that I already had from my mini equations up here. Solve for the g sub y. Integrate to find the g. Don't forget your unknown function of z. Here's my second attempt. Now I'm going to take the derivative with respect to z and set it equal to the one they had from my mini equations. Solve for the h prime. Integrate to find the h. This is not my final answer, but this is my potential function. This is my f. And so if this is my f, then because I was able to find this f, I can use the fact that this line integral, which is, I didn't read the problem. Sorry, they wanted me to find the work. That's what I was trying to do, the work. And so the work, remember, was that, this is the way it looked before, was this formula. Remember this formula? And then you would have had to do, I should have gotten something better than a pencil. I don't know how well this shows up. Okay, so then you would have had to do this for each of the 3 different paths. But notice that for this path, you would have had to have 2 separate curves, and for this path, 3 separate curves. So you would have really been doing 1, 2, 3, 4, 5, 6 different ones of these. 6 different ones of these. That's craziness. So this is so much better. My chair is making a squeaky noise if you wonder what that is. I have a rolly chair in here now, and it makes squeaky noises, but it's very comfortable, so I'm going to leave it. So try to ignore the squeaky noises. So the work to get this f, it's a decent size amount of work. However, it keeps you from having to do 6 totally separate integrals. So here, I don't even care what path I took. I just care where did I start and where did I stop. So I plug in my stopping point first, my starting point second. I had one of these values wrong, so that's why all the white out. Anyway, plug it in, 0. So here's the magic. Ready for some math magic? The other two, totally different paths. A lot of work if you do it the other way, but because this is conservative and they start and stop at the same place, ready for the magic? Just 0, still just 0. So you don't have to do any more work for B and C because this is conservative. So it's the same. So it saves you huge amounts of work with this new ways to do things, but this again only works if it's conservative. So this doesn't work for everything, but it's nice when it does work. Okay, that's all for this video. If you have any questions, send me an email.